Okay, what goes on our f of t, or our vertical axis here? That is speed in kilometers per hour. So, if we are looking at this here, it says estimate the car's speed after 2 seconds. Has anybody got a guess for me on that? What do you think the speed is after 2 seconds? Okay, around that, just a little, maybe a little above 90, right there. So about 90. That is correct. Joshua, how'd you do that so fast? Right, because this is not like the problems we were doing yesterday, right? This graph is giving us speed, right? So we're not finding the slope of this graph because the ones we were looking at yesterday gave us distance, right? So we had to find the slope to find speed yesterday. This is the speed graph. So we're just reading it right off of here. So 2 seconds, go up here a little bit above 90, right? All right, so about 90 kilometers per hour. At what time on the interval from 0 to 2.5 is the car traveling at the highest speed? So with your neighbor, see what they think. Whisper so everybody's not copying your answer. When do you think the car's going the fastest? Ask your neighbor. All right, everybody settle on an answer? Okay, anybody want to share their answer? What do you think? 2.5 seconds, do you guys agree? Right there at the end? Some of you were not because I overheard your conversations. Some of you were talking about...
At the highest speed, like overall, or like...
It won't, yeah, it's asking for...
Move the most in that amount of time.
Okay, so it's asking for highest speed. So would it be correct to say it's over here at 2.5 seconds? So this is speed, right? So this graph is giving you speed, not distance here. So the speed right here is 97 kilometers per hour, right? Over here, it is steeper. I heard you guys talking about how steep the graph is. But over here, at like maybe right here, the speed is only like 35 kilometers per hour. So since this is the speed graph, it is the graph of speed, you're just looking for where the graph is the highest. So it is going to be at 2.5 seconds. So that was tricky, and I did that on purpose because the graphs we did before, you were looking for where it was the steepest. Okay? So now, when we're talking about how steep the graph is, that does not talk about the speed. What is that talking about? That's acceleration. So the next question asks me to estimate the car's acceleration after 2 seconds. So if I go over here to 2 seconds, and I'm going to do like we did yesterday, and I'm going to try to like put a line in here that's a tangent line, a line that just barely touches the graph. Adjust it here a little bit. Let's see if I can get something that I think works pretty well. So what I'm looking for is the slope of that line would be my acceleration. So whenever you're looking at steepness, that's when your acceleration is the highest, not your speed in this case. So so if I find the slope of that, I'm going to say that's about on the line, and let's go about right here. So if we look at this, if we kind of look at how much we go up and how much we go over, this is the estimate, so it won't be perfect, but it looks like, let's see, each one of these is 10 kilometers per hour, so that's about 25 kilometers per hour, and then that is, let's see, each one of these is 2/10, so that would be 1.6 seconds, I think. So our slope is changing y over changing x. So let's use our units with it. I've got 25 kilometers per hour over 1.6. Oh gosh. If I've got kilometers per hour and then I put seconds here, I really don't want that, right? Because I'm going to end up with like kilometers per hour per second, which is not really what we want. We probably want kilometers per hour per hour. So let's change that seconds to hours first. So kilometers per hour. How did we do that yesterday to go from seconds to hours? Almost. Divide it. Yeah. So we need to do 1.6 divided by 3,600. And let's see what we get from that. That's, oh gosh, I got, this is why we don't. Alright, move that 4 places. 1, 2, 3, 4. I think that's right. Gave me scientific notation, but I think that's right. So I'm just going to do 25 divided by that number, and it is giving me 56250. Are you guys getting the same thing? It should be a pretty big number because you're dividing by a very small decimal. 0.0001. That might just, it may just, we're just going. I usually just put a lot of 4s, and it'll be close enough. Just like on the pre-cal exam on calculus, you have to be correct to 3 decimal places. So as long as you put a lot, that'll usually get you pretty close. All right, let's think about the units on this. I'm taking kilometers. Oh, I didn't mean to do that. I'm taking kilometers per hour, and I'm dividing them by hours, right? So one way you can write this is you can just say kilometers per hour per hour. In fact, a lot of times I tell kids just to do that. Kilometers per hour per hour. That's fine. Another option is you can actually work these problems out with the units. So like, if I've got kilometers divided by hours over hours, I can put that over 1. Dividing fractions is easy as pie. So I got kilometers per hour times 1 over hour. So I flip it. Flip the second and multiply. And if I multiply across on the top, I get kilometers. And on the bottom, I've got hours times hours, which is hours squared. So that'd be, I also could do kilometer per hour squared. So if I ask what time is the acceleration appear to be the highest, what would you guys say about that? When do you think the acceleration would be the highest? At the very beginning, whenever it's steepest. And if you think about, like, if you've ever had a chance to ride in a fairly fast car, or if you, you know, like most teenage drivers can turn any car into a race car just by hitting that gas as hard as you can. Whenever you take off, your acceleration is usually the highest, and that's when it throws you back in your seat. The car eventually is going to like sort of start topping out, and you're not accelerating as quickly for that. Whenever you get, particularly like this car has not topped out yet. It's got a little ways to go, but even here you can see it's not going, like 60 to 100 is going to take a lot longer than 0 to 60 in most cars. So if you've ever had a chance to ride in something fast, you'll know about that. So it appears to be, you know, at the beginning, let's just say that. Okay, so then it asks us to estimate how many g-forces we think the driver will experience at the highest acceleration. So actually, for g-forces, we really need meters per second instead of kilometers per hour per hour. I should have done that the other way, but we're not going to go back and do that because that's not when it's going the fastest anyway. It's going the fastest, you know, somewhere around here. Let's use green for this. Let's say about, let's go with these values right here. It's not a perfect straight line, but it's pretty close. So for this one, it goes 20 kilometers. Is that kilometers or meters? Have I been doing this thing wrong the whole time? No, it's kilometers per hour. Kilometers. It goes 20 kilometers per hour, and then that's 0.2 seconds. So I do, and I realize there's lots of conversions here. It's really good to learn conversions. It's not our main focus here. The first thing I want to do is I want to change 20 kilometers per hour. I want to change it to meters per second because g-forces in our, on the slide before, 9.81 meters per second squared was a g-force. So we need to change it to that. So kilometers need to go to meters. So if kilometers are on top here, I'm going to put them on bottom here, and that needs to change to meters. How many meters are in a kilometer? 1,000. That's why metric system is so much easier than your, what is it, imperial? Is that what you usually call it? But as Americans, we're stubborn. We're not going to change no matter what. Hours goes up here, and then we're changing that to seconds. So 1 hour, we've said is 3,600 seconds. So if we multiply across the top, we will get 20,000. If we multiply across the bottom, we'll get 3,600, and 20,000 divided by 3,600 is 5.5 repeating meters per second. Our kilometers are gone, our hours are gone. We got meters per second. Now, this is the speed. This is not acceleration because that's just meters per second. We're looking for acceleration, which is meters per second per second. We just had to convert this because it wasn't in meters per second. So now if I want to find the slope, instead of using 20 kilometers per hour, I'm going to use 5.5 repeating meters per second, and I'm going to divide that by the 0.2 seconds that have gone by. So this was just a conversion where I had up here on my graph that 20 kilometers, 5.5 meters per second is the same, and I got the 0.2 seconds here is my change in x. So now if I do this, divide by 0.2, I've got 27.7 repeating, and that would be meters per second or meters per second squared. This is my acceleration.
Where did the 0.2 come from?
Each one of these little blocks up here on the graph is 0.2 since it goes over here to 1. So, so my change in y is at 20. My change in x is the 0.2 there. Okay, so this is acceleration. So if I want to know how many g-forces that is that are like throwing you back in your seat, I'm just going to take 27.7 repeating and divide it by 9.81 because that's how many, that's our acceleration due to gravity. So if I do that, 9.81 divided the division there, I get 2.83. So if you ever got a chance to ride in a car like this and have it really take off as fast as it would go, it'd be getting close to 3 Gs that would throw you that. Okay. Of course, that is just like in one direction there, which if you're just taking off like drag racing in a car, that would be all you would have. Roller coasters, of course, are going to be much more complex than that because roller coasters don't just drag race, right? Roller coasters go left, right, up, down, everything. So you've got G-forces in a lot of different directions. So the physics of that would have to be significantly more complicated than just looking at one direction. I guess I should put G's here. So, if you ever get to ride one, this is what you can expect. I doubt I will have the chance, but if any of you become roller coaster designers, if you own a company that makes roller coasters and you are going to come back anyway in your Porsche to tell us about it, maybe you can take me for a ride. We went to Germany this summer and got to go on the Autobahn, and I was really wanting a car like that to come like whipping past us at like 150 miles an hour, but it did not. Cars were going pretty fast, but no like Lamborghinis just passing us as fast as they could go. I was kind of hoping. We did see a Lamborghini, but it was like in town. It wasn't going fast. It wasn't on the Autobahn. So, actually, I saw a Lamborghini at Los Munchies the other day too. It was pulling in, white one. So, not sure who that was, but yeah, but there was a Lamborghini there for sure. So Germany's not got anything on us here in Elkin. Okay. I don't want to do this one. Yeah, let's do this one because I want you to see another context to something like this besides just like speed and velocity and acceleration, because there are a lot of other things. So I made this problem up back when Miss Hurl was the librarian, before Miss Wallace was the librarian, before Miss Husky was the librarian, and before we just didn't have one at all anymore. So we've gone through a lot since I made. She's here. Yeah, she's got some sort of seat where Miss Phelps left. You guys, yeah. Well, she had been just doing testing, so you guys probably didn't see her a whole lot anymore. Yeah, but you did see her during testing. But she, I think, moved to Burlington, maybe. So she left, and we're broke. If you haven't heard, we're broke. So rather than replace her, Miss Husky took some of her responsibilities, and Miss Carpenter has some of the stuff that she did as well. So
But
she is.
now we just don't have a library.
Yeah, so now, I mean, the library's still there. I think they are going to have somebody in there in the mornings. Not a librarian, obviously, just somebody to check out books. Like, if you do need a book or something, there'll be somebody there in the mornings and during EHS
Other than
time.
checking out books, though, what does the library like really do? Like,
Just
for
watches
us?
the kids.
Yeah.
Yeah,
I'm not ever like, I'm going to ask the librarian for any suggestions.
Yeah, I think that the idea is that they will, like, give you book suggestions, or sometimes they'll, like, work with teachers. Yeah. And, like, when I was in school, when you did, like, a research paper, you went and looked in books to do your research paper. There was some online stuff, but not like it is now. So,
We have so much more online than we have available in that library.
yeah.
A bunch of people.
Yeah.
One wall book.
Yeah. So I don't know. I think that, like, that's a good place to have, and having somebody in there to organize everything is important.
They have like online classes you could go and
Yeah. Yeah, we have. We don't, if you have an online class and you don't want to go home, the two places that they said that you can be are in guidance or right out here outside of my room. Yeah. Because right here, Miss Carpenter's there a lot where she can kind of watch you. They've got you on camera. They can hear you from, there's technically not somebody there watching the whole time, but Miss Hankins can see you. Yeah. So if a fight breaks out, then I'm on my way. If I hear you. So, yeah. So, the gym actually has nothing to do with it. We rent here. Let's pause. Emma, I'm gonna pause this because I don't think you need to know about our money transfer. Deadline, number of books missing. So she's trying to get the books before summer begins. So we have the number of books that are missing. This is cumulative. So this is 10 days before the deadline. So days. Hold on. Let me read what I've written here. I don't think it makes sense, does it? Trying to get all the books returned to the library before summer begins. It is 10 days before the deadline. The number of books still missing is given below.
They should go the other way.
They should go the other way, shouldn't they? Or I should. Let's just change this. Let's just make this say, like, day. So, like, on day 0, that's going to be 10 days. And then day 2 is after 2 days of collecting books, and 3 and 4. So we'll keep the numbers the same. Let's just change our heading so that it makes more sense. Okay, so you can see on the first day there's 82 books missing, and then 72, 63, and so on. So if we were going to estimate the rate at which books were returned in books per day on day 1, right? So on day 1, if we think about graphing this, we'd have days across the bottom. We'd have books vertical, right? So we want to know how many books approximately were returned, or the rate for that on day 1. So 1 is not on our list here. What we're going to do if we want to estimate this, we want to know in books per day. So if this is books and this is day, we want change in books over change in days. That's the slope that we're looking for. So we will have, the best thing to do is get the slope of the points closest to 1. So in this case, 1 would fall right here between 0 and 2. So what we're going to look at is, you can think of it a couple ways, like change in y over change in x, or this is also, does anybody remember the slope formula for the points? Like if I have the point, what is it? y2 minus y1 over x2 minus x1. So if I think of these as points, 0, 82, and then we've got 2, 75. So we would have here 75 minus 82 over 2 minus 0, and that is going to give us negative 7 over 2, so negative 3.5. When you're talking about units for this, this was measured in books, and this was measured in days, so this is negative 3.5 books per day. Okay, why is it negative?
Because there are
Less books. So we're decreasing, right? So our slope is going to be negative because our values are decreasing. Right. Very good. Okay. We want to also estimate the rate at which books were returned on day 7. Okay. So if we're wanting to use day 7, 7 falls between 5 and 8, but not perfectly, right? At least up here, 1 was halfway between. This is not perfectly between, but it's still the best we can do, right? To go between 5 and 8. So we would do something similar here. We've got those points are like 5, 52, and 8, 30. And so I would do 30 minus 52 over 8 minus 5. And so that is going to give me negative 22 over 3. And let's put decimal for that. 7.3. Repeating, I should have known that in my head. Negative, and this is in books, per day. So we could look at all of the intervals, but that would just take too long. It appears, at least from our two that we have looked at, that on day 1, we're not getting books back as fast as we are on day 7, which if the patterns I have seen among student behavior hold true, why turn in something now when you can just wait till the very last minute? That seems to be how most students operate, so, or lots of them anyway. No, he was one of these 3.5 right here. Hunter Hyatt, he's one of the 12 right here. This morning he asked me to sign a paper on the way to school while I was driving, and acted like it was an urgent matter. And I told him I would sign it when we got to school, and he was like putting it in front of my face at the stoplight. I was like, Hunter, it will not hurt to wait till we get to school. So.